Everyone. Thank you for joining our talk about Apache Liminal incubating. First off, a quick round of introductions. My name is Assaf bin Khassi. I've been working in the intersection between data, machine learning, and engineering for the past 20 years. These days, I'm an MLOps and data engineering consultant working with a number of companies. And previously, I held the role of Director of Machine Learning and Data Platform at PayPal, and as well as a VP of R&D at a company named Zebra Medical Vision, the field of medical imaging using deep learning for computer vision. And I'm a PPMC member of Apache Liminal. And with me is my colleague Aviem. Aviem is a data architect at Natural Intelligence, an Israeli company. He's a PPMC member of Apache Liminal, a PMC member of Apache Beam. So here we are. And our agenda is, I'm going to walk you through quickly some of the challenges in orchestrating machine learning pipelines, and I'll review a few of the existing tools out there. And later, VM will kind of explain to you how Liminal addresses the challenges, as well as do a deep dive and a demo. So let's get started right away. This is a slide that I took from Martin Fowler describing the process of developing and deploying machine learning products. Those of you might notice that this flow is missing a very, very important piece, which is the data work. So let's add that. And I'm going to walk you through it really, really quickly. So first off, every machine learning project starts with data engineering work. It can be ingestion, it can be building features, etc. The research itself or trying to solve the machine learning problem typically starts with a phase called research, where a data scientist would be trying out different ideas. It can be different model architectures, different feature combinations, different dataset compositions, metrics, etc. Once an initial model has been built and seems to be working reasonably okay, typically the data scientist would go through cycles of model evaluation and experimentation in an attempt to improve on it or maximize its performance relative to the metrics. This can be hyperparameter tuning, or it can be going back to feature engineering to try and find more signal in the data, etc. Once a model has been developed and tuned and is now considered optimal, we go through a few steps of actually preparing it for production. So first of all is what we call productionizing the model. So it could be removing dead code branches that made their way into our code base. It could be kind of compiling the model or funneling it through some sort of a framework that optimizes its speed for inference and other steps such as these that transition from an experiment to something that looks like production-ready code. Then in machine learning, there's typically a more elaborate phase of testing that can cover any number of things, from large-scale regression testing to verify that the new model is performing at least as well as the previous one if it's a model refresh, all through verifying the metrics officially on the fully productionized model to make sure that it does indeed perform as we expect, or doing bias analysis, etc. Now, once the model has passed all the tests, we need to basically bake it into some sort of a production component that is able to use it for making, actually for inference. So it could be, in this case, it could be that we need to bake it into some sort of a wrapper in some sort of a REST API, either within an existing service or within its own service, or we could deploy it into a batch pipeline that does inference in batch. And finally, we monitor the model in production. We make sure that its performance meets our expectation also once it's been released. So this process is non-linear, so phases can go back. We can go back to feature engineering after testing failed, and but this is roughly the steps that we take in order to deliver a model to production. Now, one thing that I'd like to draw attention to is what happens if after a month in production, which is quite a common scenario, the model starts performing or underperforming. It could be anything from data drift to concept drift to new behaviors that the model will now need to be trained on in order to capture the performance that we need. Um, how do we actually um, how do we actually go back to the beginning of this process and repeat it in order to tune our model or improve it slightly um, for our next iteration of production? So once upon a time, data scientists used to basically develop their models in Python notebooks or uncommitted Python files, and really walk through this process manually, step by step, until they had a binary file representing the model, and then hand it over to the engineering team. This was both very error prone. It occupied the data scientist in work that's kind of mechanical, and it was very risky. Um, so these days we have something better, which is called using MLOps. We define MLOps as really the efforts to operationalize the machine learning lifecycle. But once we have a mature enough process for training a model for a specific problem, we should be able to automate it to make it repeatable. The automation can be trivial, just like run through the steps one after the other without any kind of brain, or it can contain steps that actually optimize or tune the model automatically, but still automating it, obviously to save costs, reduce human error, and increase speed and quality. Now, the automation process obviously draws a lot from best engineering best practices, but it has to be adapted somewhat to the specifics of machine learning pipeline and automation. So let's see what are some of the unique challenges that we're going to be facing here. So the first challenge is really the stack. Okay, I'm going to very quickly just demonstrate here. So for the data engineering piece, we have a number of technologies that we might already be used to using and that have best practices for how to automate them into a pipeline. But one of the first decisions we need to decide is where are we going to store the data generated by the data pipelines so that the model can train on it. There are concepts such as feature stores, or there are concepts such as data version control tools that are specific to machine learning that we need to integrate with. For the actual model building itself, there are a number of frameworks and tools to do the actual model building itself, be it TensorFlow or scikit-learn or PyTorch or Ray. And then for the experimentation side, we have tools that help us with hyperparameter tuning, help us with dashboard and tracking the progress of the model, as well as tracking our experiments to make sure that we're able to reproduce them once we have a good enough model that we'd like to actually productionize. In the productionization space, we have a number of tools that optimize models performance, for example, as well as tools that help us package a model as an artifact, an official artifact, rather than just a binary pickled file. And then for the testing side, here the tools are relatively, there aren't just quite as many, but there are quite a few tools that we can use to kind of verify various properties of our model, understand why is it behaving the way it's behaving, and kind of generally debug it. When we get to the packaging for production, inference frameworks there are quite a few of them that help you supposedly from moving from having a packaged model or a binary file with model weights to having a fully fledged service running in production that can do swaps between model versions, etc., etc., and actually be production grade, as well as the feature store has another aspect that appears here in production if you need to access real-time features while you're doing inference. And then lastly, for the model to be operationalized in production, somebody needs to monitor it, and there are tools that are dedicated for monitoring machine learning models that look at different things from kind of operational monitoring, standard operational monitoring. And all this stack is sitting on top of distributed computing frameworks, for example, Kubernetes and Docker, which need to be also monitored by themselves. So the first impression here is that there's a huge variability in terms of the number of tools and frameworks that we need to integrate with the technologies, GPUs, notebooks, and inference in production. It's really very diversified. And the second piece is like when we think about automating, we need to ask ourselves who is going to be the person automating this pipeline, right? Data scientists are usually not trained for this kind of work and also sometimes lack the inclination. Um, and backend engineers or data engineers often lack the context of what the machine learning pipeline is actually attempting to do and what is the meaning of each step and did it work or didn't work. So we have a gap here also in talent. And lastly, even once we did synchronize and orchestrate this entire pipeline somehow, things tend to be dynamic. So it could be that next month the data scientists would want to introduce ensemble model ensembling and actually train a number of different models, each with its own life cycle, and then ensemble them into the final model result. And all this flow is going to need to change somewhat, or there could be new best practice for model profiling, which need to be introduced to the pipeline. So really, if we want to summarize the challenges, they're really around variability. So there's a various standards out there for what's the best practice for this workflow, for the steps in the workflow. Infrastructure is very diverse, and new tools and frameworks keep coming out daily. And there's also the persona and skill set diversity challenge between data scientists, engineers, DevOps, etc. Now, since engineering automation typically rely on some sort of an abstraction in order to be effective, we need to ask ourselves, how do we create abstraction in the face of such a huge diversity? So first I'll describe an approach that we didn't take, which is what we call the integrated platform approach. The idea here is very simple. Some tools want to offer an end-to-end solution for machine learning pipeline, tools that are kind of opinionated about how, which infra you should run on, how your process should look like, and what are the tools that you need to use inside each of these steps of your workflow. And by doing so, they kind of formalize the interface between steps or tasks of the pipeline and reduce variability. Hence, are able to capture the abstractions well. So I'm going to walk you through a number of tools that do that in kind of integrated platform approach. The column that we want to be looking at is the orchestration piece, which is the focus of this call, but also I'll exemplify how the integration works. So first off, let's look at MLflow out of Databricks. Databricks obviously would mainly run on Spark. They have a solution for the data. Of course, they use Spark, but they offer Spark ML as the framework for building models. They offer notebook servers for actually experimentation. They have an experiment tracking system, a model packaging format. They even dabbled in model serving as REST APIs. And they have Databricks Jobs as their orchestration engine. Next up is Kubeflow, quite a popular project out of Google. Kubeflow is really centered around Kubernetes. It assumes that every single step of the process is a Kubernetes task. And Kubeflow is more open, so the implementation of steps can be provided by the community. But yeah, it does offer a notebook service. It offers ready-made machine learning containers for the training, hyperparameter tuning, experiment tracking is integrated into the tool. There's an inference piece with multiple frameworks that can be plugged in, each with they have follow kind of a common interface. And in terms of the pipeline, they offer a tool called Kubeflow Pipelines, which orchestrates all this workflow, as well as there's a tool called Kale, which takes a notebook and turns it into a Kubeflow pipeline. Next up is SageMaker, maybe the best example for an end-to-end platform, because they really touched on each and every step of the pipeline. They keep adding more and more stuff. For the data, they've recently added feature stores. They provide VMs, images for training. They have their own packaging format, experiment tracking system, inference service. Of course, SageMaker performs inference as well. And they have recently released something called SageMaker pipelines for the orchestration. And last but not least, Vertex AI out of Google, which is really based on Kubeflow open source, but in a managed format and really well integrated with the entire GCP stack. So for data engineering, they offer managed notebooks. They offer TensorFlow extended for easily accessible explainability, fairness, and debugging tools. They have TensorFlow as a packaging format. They have managed inference service. They even have a service that does continuous evaluation of model in production. And their orchestration tool is based on, basically, it's a managed Kubeflow pipeline solution. So here, these are good examples for the approach of let's try and take the machine learning pipeline and create uniformity in it, be opinionated about how it's actually being run. And but Apache Liminal took a slightly different approach. The idea here is that we want to embrace the variability. So in terms of diversity in standards, we're focused mainly on the orchestration piece versus the implementation of the steps themselves. We're not so opinionated about how machine learning steps or processes need to look like exactly. Regarding the infrastructure and tools, first of all, variability or diversity is good for the community, but we wanted to start off from existing open source orchestration tools that already deal with a lot of the diversity and rely on the community to add support for anything that's unique or new that's specific to machine learning. And last but not least, the diversity in skill set. We basically, the approach here is to separate and divide and conquer. Data scientists should focus on declaring their machine learning system or pipeline, which they are able to also test locally without needing to understand infrastructure, as well as, of course, provide the implementation of the machine learning steps. And engineers should be focused on configuring and exposing the infrastructure for the machine learning pipeline, while maintaining a very, very clear interface between the two roles so that they can understand each other and reason about the system. So at a glance, data scientists that use Liminal provides code and dependencies for the task implementation and declares their pipeline using a YAML file. An engineer who supports the pipeline is able to configure the infrastructure, be it Spark clusters, Kubernetes, etc., using YAMLs as well. And Liminal itself fuses the infrastructure and task definitions together and basically creates an Airflow DAG. The DAG runs each machine learning task as an Airflow operator, which can run on Docker, Kubernetes, or Spark. And of course, new implementations for both steps and for orchestration pipelines are possible. So now I'm going to hand over to my colleague Aviem, who will walk you through the details of Liminal and exactly how it's implemented and show you a demo.
Thank you, Assaf. Hello, everyone. My name is Aviem, and what I'd like to do now is take you on a technical dive into Liminal. So, as Assaf mentioned, we want to create an abstraction layer between the user and the infra where the user's code will ultimately be running. The way we achieve this is by defining a data system in a configuration file we call liminal YAML, and we ask the user to include this file in their code repository alongside their code. But other than adding this file, we don't require them to change anything about their code. So we simply add a file next to it. So what does this file look like? Let's have a look at the anatomy of a liminal YAML file. So here you can see we have a name and an owner, and these next 4 sections, which we will dive into now. So the first section is rather simple. We have variables. So in this section, you can define variables to reuse in later configurations. So as you can see here, we have myvar1 and myvar2, and we can reuse those later. The next section is images, where we help users build their code as Docker images without having to know anything about Docker. All they need to supply is a simple configuration of an image name, an image type, and what source code they want to include in the image. So we have several image types, such as Python and Java, and another interesting one you can see here called Python server. So what is the image type Python server? With this image type, they can build their code as an HTTP server without having to know how to do that or change anything about their code or requirements. So how do they do that? They define another section here called endpoints, in which they map the endpoints of the HTTP server we're going to build here. So they give an endpoint path, in this case, my endpoint, and they provide which module and which function of their code should be invoked when a client accesses this endpoint in the server. Now, this function doesn't need to be anything spectacular. It's just a function that receives a string input, a body of the message, and returns a string output as the result. So as simple as that, they create a server. This is good, for instance, for creating real-time inference servers. So if we have code which trains data science models and we want to serve them to clients within our organization, we can easily do that with an HTTP server, which will then receive requests for real-time inference and return response, which are model predictions. The next section we see here is a pipeline section, in which we define a set of pipelines for our application. So what is a pipeline? A pipeline is an application that runs on a schedule and executes a list of tasks sequentially, one after the other. So we can see the definition here. We have a pipeline, my data pipeline, timeout, start date, a schedule using a cron expression for when this application should run, and then a list of tasks. We have two Python tasks here. So the first Python tasks uses the Python image that we built in the previous section of the images. So we use Python app, and we run the command execute the Python file, myPython module1. We also want to pass environment variables to the Docker container, which will be running this image eventually. So here we define an environment variable called myEnvVar, and we pass it a value, the value of the variable that we have defined earlier in the variable section, myVar1. So the value here will be myval1. Same with the second task here, myPython task 2. We run a Python file called myPython module2. And for the envar, myEnvvar, we pass the value of myvar2, which in the variable section is defined to be myval2. So simple as that, they can define a pipeline, which will be executed on the proper infrastructure, which we will talk about a bit later. The final section I want to show you here is the monitoring section, where the user can simply define metrics and alerts backend, and Liminal will take those and automatically produce metrics regarding the running of their pipelines, as well as alerts in case the pipelines are misbehaving in production. So the metrics we automatically send are job started, job status, so when it ends, 0 or 1 for success or failure, and job duration, how long the pipeline execution took. And we have different providers of metric backends and alerts backends. In this example, we can see we use Amazon's CloudWatch service. And we define what needs to be defined for the metrics backend. And when Liminal runs the pipeline, it will produce the metrics to this backend. And we define an alerts backend, which uses the metrics backend that we defined above and creates alerts on top of those metrics. Here we define configuration specific to CloudWatch, which is what to do in case of an alarm, what to do in case of an OK status. You invoke some sort of ARN that you configure here. And Liminal uses the alerts backends to register 3 types of alerts. The first alert is application failed. Very simple. If the application sent that it has a job status of failure, you'll get an alert that application failed. And the next alert it defines is application took too long. So if the duration of the application exceeds either a configuration by the user or by default the scheduling interval between 2 subsequent runs. then we will get an alert that the duration is too long, because that is not sustainable. The final alert, and the most important, is application is not running on schedule. So this is one where a lot of infrastructure today misses this. So you cannot rely on your application actually to be running and see if you get metrics that it failed or not. You need to know that it is actually running on the schedule. So again, we use the schedule interval between two runs. And if there has not been an application run within that interval, we will get an alert that application is not running on schedule. So that's how we define a data system. Pretty simple. How do we translate this to running user code on infrastructure using Liminal? So let's see an example. Here is a Liminal setup that we use at the company I work at, Natural Intelligence. And we will show you how we take the Liminal configuration file and deploy the user's code in production environments. So here we can see the user experience. So as we saw before, they create a Liminal YAML file in their code repository and commit it along with their code repository to their source code repository. In this case, GitHub is what we use. From there, a CI pipeline is triggered on Jenkins. And on Jenkins, we use Liminal to do three things. We build code, and we build the user code into images and services, which are also images, as we saw before. What do we do with these artifacts that we create? So once we create them, we upload them to the relevant locations. So in case of images, we push them to Docker Hub using the Jenkins pipeline. And if it's Spark jobs or other big data jobs that we use within an organization, then we upload those as jars to Amazon S3. When we want to deploy to production, we use Jenkins to do the deployment, and we deploy images that are services that we want to run in production to Kubernetes. So we have Jenkins code, which uses the image that Liminal built, and we deploy it as a service on Kubernetes. In order to deploy pipelines, we use Apache Airflow as our pipeline runner. So the way to deploy to Airflow is we use Jenkins to upload the Liminal YAML file that the user created to a running instance of Airflow that we have. On this instance, we have Liminal installed, and Liminal reads this configuration file, Liminal YAML, and uses the pipeline configurations there to register pipelines as Airflow DAGs. In the future, we can implement other pipeline runners, but currently we use Apache Airflow exclusively. And if we need to execute big data jobs, we submit those to Amazon EMR. The last section, monitoring, as we saw before. So as we said, Liminal is executing the pipelines and reporting metrics to the various metrics and alerts backends that we use at Natural Intelligence, where it reports the metrics to and registers alerts on to have production quality, production grade applications. One more thing that we didn't mention here is when we want to run user code, then the pipeline will launch a pod on Kubernetes, which will use the image that the user created to run their user code on Kubernetes. So that's the translation to infrastructure, very simple. And all of this is abstracted away from the user. So the user doesn't need to know anything in this stack or have experience or expertise in any of them to be able to have a production-grade application which is running in their organization. So that's really great power that we give our users. And what we'd like to do now is a short demo of a data science app which will train a linear regression model to predict if a given flower is of genus Iris virginica. So how do we do this? We have an example Python project here. You have, as usual, Python files and requirements text. And as we mentioned, we ask them to add one more file, which is the Liminal YAML configuration. So what does that look like for this application? We have my data science app. We define one image of type Python server. We give it a name and source the entire repository, so dot. And endpoints, we define one endpoint called predict, which will invoke module serving.py. and a function there called predict. We also define a pipeline for training a data science model to then be used in the prediction server. So what does this pipeline look like? It has a name and a schedule and all the configurations we saw before, and it runs two tasks. It runs the train task by using training.py and passing it the argument train, and it does a validation task, which validates the model and deploys it, and it does that by running training.py and passing it validate as an argument. Now, as you can see here, we're using the image, my data science app, which is the same image we defined here for Python server. So we can reuse Python servers images as Python images to just execute whichever command we want. Regardless that this image also has the capability of running a server, you can also just run user code within it. So you only define one image in this example. The code of the application, here we have a rudimentary model store for the sake of this presentation, and nothing production grade, just an example. So we have a production model store and a candidate model store, which we can save models to and load latest model from. A requirements text, so it's a basic data science app. It has two dependencies here, scikit and boto, as well as Liminal, which is optional. You don't have to add it to your requirements, but if you want easy access to Liminal CLI, you can install it via your requirements file. We have serving, so the function predict that we saw earlier. We have a definition of predict, which receives a string, an input body of the request, which in our contract here, we expect it to be a JSON. So we load the input as a JSON. We fetch the latest model from the production model store, which we define up here. And then we use that model to predict the probability that the given input of a flower is of genus Iris virginica by passing it arguments of the input received, in this case, petal width. And then we return the result as a probability of that flower being of genus Iris virginica back to the client. Here's the training model. So boilerplate sklearn code using the sklearn public dataset of Iris, of the flowers. And we train a logistic regression model to see if a specific flower is of genus Iris virginica. We save it to a candidate model store. In the validate section, the next task in our pipeline, we load the latest model from the candidate model store, perform validations on it to see that is it performing correctly. And if all passes all the validations, then we save that model to a production model store, which, as we saw before, the serving layer becomes aware of it because it fetches the latest model whenever it's called. Here's an example of the CLI that we would use to test this application locally and within Jenkins to build artifacts. In our case, our CI uses Jenkins, so it uses Liminal CLI. So we have Liminal build to build Docker images from user code, Liminal deploy to deploy Liminal YAML files to a local Liminal server. So the default local Liminal server right now is Apache Airflow with Liminal installed on it. And we can do Liminal create to create volumes, which we did not cover in this presentation. And Liminal start, which will start the Liminal server, or the Apache Airflow server in this default case. This is what in pipeline looks like when it's running on Airflow as a DAG. So we have a start task, which reports metrics, which is generated automatically by Liminal, followed by the user tasks that we saw, train and validate, and an end task again, which Liminal uses to send metrics as well. Here's an example of a request to our server. So we run the server locally in this example and access the endpoint predict, passing this the following body, information about a flower. So this flower has petal width 2.1. And the response from the server is the probability of this flower being Iris virginica, in this case, 87%. And that's it. We can see the server logs here. We use Flask to create the server in Liminal. We can see the input that was sent to the server, that it loaded the latest model, and returned the result that we saw. So we use this to empower users of Liminal to create data systems that are complex, that have different underlying infrastructure that they do not need to be aware of, and a production-grade applications which are monitored, which is most organizations' first need for an application to be allowed in production. So all this is great, but what's next for us? Well, we want to provide CI integrations out of the box with Liminal for platforms such as Jenkins CI. We want to create a user interface, so the server that we will start will be a Liminal server, and it will have a user interface in which users can create pipelines and applications via a wizard instead of a configuration file. We want to integrate with known ML packages, as well as experiment tracking, support all clouds natively, and perhaps even provide a layer of model store that will come out of the box with Liminal for organizations which do not have model store solution. And in the center of it all is the open source community. So we need you in order to complete our roadmap of everything we want to do with Liminal and make it great. We need a community around it, which is why we started it as a project in the Apache incubator. And we invite all of you to come and join us and help us in this endeavor. We are eager for contributions, and we are very accepting. So if anybody is interested, please join the effort. And you can do that on our website and join our mailing lists. You can go on Apache's GitHub to the project incubator Liminal, and you can see tasks related to the project on Apache's Jira server. The project name is Liminal. And that's it. So for Assaf and for myself, I say to you, thank you for watching this presentation and hope to see you in the mailing lists and on GitHub. Thanks, everybody.